Díomh inniuh tá chun fécint C3 surface geometry or Gauvíle sa Shadek. So today we're going to look at the surface geometry question from 2016. So the image on the right shows a package of jelly beans. The package consists of a cardboard transition piece connecting a square base to a circular top. This transition is achieved using triangulation as shown. Figure C3a shows the plan and elevation of the package and also shows the triangular division. A partial surface development of the triangulated transition piece is given in figure C3b. We'll have a look at those in a minute. What we're asked to do is to draw the given plan and elevation to include a straight line element on the curved surface as shown. Draw the true shape of surface ACE and determine the true length of the straight line element AF, showing all necessary constructions. Hence draw the given partial surface development of the transition piece. And part D then, as the design feature, the base is indented to form a pyramid as identified by the hidden detail. Determine the dihedral angle between the triangular surface ABC and ABD. Okay, so there's a few things, there's a lot asked in this question, but some of it is taking us back to our junior cert graphics, finding the true shape of a surface, and then the dihedral angle we've covered in section B as well. Right, so if we look at, we have our elevation and we have our plan here. They show us a lot of constructions and what they want us to do in it. Okay, so they give us the angle that the square is at. They give us the length of the side, so we know this side has to be 60 as well. They also give us the heights here. All right, they label a lot of the points for us, so we know where they are here as well. So part A we should all be able to do. All right, part B then as well is given here. Now they don't have any of the measurements on this because we have to find those, but they show us what it should look like. Alright, so if you look here, the line is slightly curved up from E to H. Right, so that's the development. That's what it's going to look like because it's built using triangulation. Alright, so we're going to go over to the question now and we're going to answer the question. Okay, so if we look at here, we're going to draw our base. That's where we started. Okay, so it's a square 60 millimeters long each side. Okay, we're going to draw our circle inside in the square then. Right, we'll label all our points, project them up. We have our height line, so we know where our points are going to go to. Alright, so the development will be drawn using triangulation. Divide the surface into a series of triangles as shown. So if we look back to our question, they divided it up down here. Alright, you can see the divisions. Right, we're going to do the exact same thing here. Okay. So this is just in the graphic here, it's just showing us our triangulation. We divide it up and we're getting our points then on the circle at the top. Okay, so this, again, the circle is at the top, the square is at the bottom. Right, so they're all our points on the top. Okay, so that shows us our triangulation. So before constructing the development, we must first determine the true length of the triangle AF and AE. AG and AH are the same lengths as AF and AE. Alright, so if we look at it here, AF and AE, right, they're the two we're looking for. AG and AH are the exact same as the other two, okay, because it's a symmetrical shape, right? You should see that from here as well. So what they're saying is AF is the same as AG and AE is the same as AH. True length can be found by rotating the line AE until it's horizontal in plan, okay, so we're getting a level line here. Okay, so we're going to rotate this down until it's level here. Okay, so you'd see that happening now. Okay, so we're rotating E down till it hits here, and we're going to project it up then. When we redraw the line in elevation, it will be a true length. Okay, so we're coming from A to E. So we've literally pulled this line down here, and we're going to do the same thing here. So we've drawn it out. Okay, so E is now here. Okay, the width of AE in plan can also be used to determine the true length as shown. Okay, so just what we're literally doing here is we're just drawing it out here so it's not as messy on top of the drawing. Okay, so that's the distance AE. What we've done, we've just drawn any line. It doesn't matter the distance from here to here, it doesn't matter. We've got the distance from A to E and we've marked it out here, and we'll join that back to the baseline here. Okay, so this point here is A down at the bottom now. Repeat to locate the true length of AF. So what we're literally doing now, we're going to draw F onto the line E. Okay, so from A to F, we're going to get our compass, we're going to mark it onto the line E. We're going to get our distance then from A to where F is, and we're going to mark it from the point here out. Okay, so that's given us the distance from A to F. All right, so again, we said already, AF is the same as AG and AE is the same as AH. So we don't need to find those. All right. So construct the development of surface ACE using the true lengths. All right. So we have the true lengths now. These are all true lengths. All right, because we got it as a level line down here in plan. All right. We projected it up. We had our heights from up here. Okay. So ACE, we're going to get from C. We're going to get our distance from A to E, because CE will be the exact same as well. And we're going to do the same from A. So we're going to mark it with our compass where they meet. Then it's going to be the top where E is. Okay, so that's ACE. All right, that's the first part of the development. So we need to measure the distance from E to F in the plan and mark the distance from E in the development. So the distance from E to F is here. So it's one section of the circle. All right, so we're going to mark that off up here. So see it here? One sector of the circle, we're marking that off, and we're getting the true length then of A to F. Okay, so we're getting this line, we're marking it off where it hits it. Okay, going to do the exact same for G. So F to G is going to be the same distance. Mark that off, and we're using the same length because A to F is the same as A to G. And then for the last one, we're using the length, we're going A to H, so we're using the A to E one we had, because AE is the same as AH. So the length, that's why it curves up a little when it gets to H. Okay, so you'll see it there, it curves up a little, that's why that true length is a bit longer. Okay, dihedral angle now. Alright, so there's two methods of this. There's the rebatment method and there's the method we always use as well, looking at it perpendicular. I'll go through this method very quickly. You don't need to do this method, you can do the method we always do. So produce a true length of the line intersection by looking perpendicular to AB. Okay, so we're looking perpendicular. A cutting plane will cut the planes perpendicular to the line of intersection. So rebat the cutting plane until flat on the horizontal plane. Okay, so we're going to rotate this down, yeah. Okay. So draw the rebatted cutting plane in plan to determine the dihedral angle. So what we're literally doing is, imagine this is on a hinge here and we've rotated it down. Okay. So what we've done is we've rotated it down, we've located the base of it here and the top of it here where it hits it. And that's going to be our dihedral angle in there, okay? Don't worry too much about that. This is the method we always do, the edge view method, okay? The dihedral angle can be seen when the planes ABC and ABD are seen as edge views. If we look along the true length of the line of intersection, the planes will be seen as two edges locating an angle between them. A second auxiliary is produced looking along the true length. Okay, so the xy is perpendicular to the true length. Dimensions are taken from x1, y1 to the planned dimensions. Okay, so we should all know this. Alright, so we're perpendicular to the line AB, parallel for our x1, y1 here, and then perpendicular here. Okay. Getting our distances. Then that's our dihedral angle. And that's the question done. Okay. Any questions, please let me know.